Okay, I think with it being 5 after, I'm going to get started. And I don't intend to use the whole hour and a half here because I'd like people to be able to have a chance to have lunch and do any various other things, depending on what time zone you're in. I'll just introduce myself real quick. For those who haven't heard me prattle on about this before, I'm Joan O'Mara. I'm the chief scientist here at Keck. And we've got a number of other Keckies here on the line and a number of folks from Nexi as well. And I don't have a presentation that's intended to last the entire session, far from it. I would much rather use the time to have a bit of back and forth to talk about various aspects of DSI. But for those of you who have not heard me talk about DSI, I'm going to give you just sort of the philosophical reason behind it. This is in many ways brought out by my experience as a longtime Keck observer. If you saw the previous session on Kodiak, you might have heard Nicola Lehner mention that I'm the chief data person for Kodiak. And what that really translates into was spending many, many, many years diving into the Keck archive and re-reducing the data and turning it into sort of a science usable form. And one can ask the question, should that be the way that people access data from the archive? Perhaps the answer is no. So that's part of the philosophical introduction to DSI. Before I get started, I want to give out some kudos to people who are doing significantly more work on this than I am. I just sort of sit and give presentations and babble a lot. Luca Rizzi, who is really sort of the main philosophical thrust behind DSI at Keck. And he is the lead of a number of aspects of DSI, including the integration with data reduction pipelines. Jeff Mader at WMKO, who is going to be leading most of the infrastructure backend development that's going to be needed for many aspects of DSI. And then a large number of people, including staff astronomers and our software teams here at Keck, who are going to be doing a lot of the development. We're going to be hiring some new people to come in. And in addition, this all doesn't work unless we have the data being served at the KOA at Nexi. And I noticed that Bruce Berryman and Chris Giolino are on this call. They're two of the people who make it all happen over at KOA. And finally, some kudos out to NASA headquarters, who have been one of the key funding partners in DSI going forward, along with members of our community. In fact, I missed a bullet here to the kudos to all the people who are working on data pipelines out in the community and with the various instrument teams. So I want to just give a little bit of a motivation for this, which is, here is what I view the current state of most large ground-based telescope archives to be, which is that they're bit buckets. If you go to most archives for the ground, this is not true for space in any way, that most archives tend to store the raw data, some enhanced data products, some extracted products, but they're really mostly a repository for bits, especially for classically scheduled observatories like Keck. This is even more so the case. The KOA has, over recent years, really started to change this by having more and more reduced data products in the archive. But by and large, they're largely repositories for raw data. And at the same time, the current state of most data reduction pipelines is given by this. They're very much roll your own. For those of you who use Keck data, for example, many of the pipelines, most of the pipelines, in fact, are pipelines that have been developed by individual observing teams or instrument teams, but which are not necessarily fully supported by the observatory. And in many cases, those data reduction pipelines have been developed for a specific science purpose, not really to be a general use data reduction pipeline for a Swiss Army knife-like instrument, kind of like LRES, for example. Sometimes people might write a data reduction pipeline purely for point source quasars or something like that, and don't really have an eye towards general utility. And so DSI philosophically is meant to address both of those things, because these are the two externally facing aspects of data at Keck to the community. So we have to go beyond the bucket and the data bucket for the following reasons. We really need to expand the community of people who use Keck, because we've got fantastic data, as you've been hearing here over the last few days. And we want to be a better partner with our partner institutions and with new partners to be able to bring more accessibility to the data, more usability to the data. And we want to be ready. We want to have a system that is ready for the data avalanche that's going to be coming once Rubin Observatory goes online, once Roman goes up in space, once Euclid comes along. All of these missions are going to be releasing data that's going to be very important to live in harmony with Keck data and the synergy that happens between those data. But the volumes of that data is so large that we need to be ready on our end to have people be spending more time studying their data than they are reducing it. And you have to go beyond roll your own for the exact same reasons. We want to be able to expand our community, which means if you're spending 6 months learning how to use an obscure pipeline and not using those 6 months to study the data, you're not getting the most out of your time. And that's lends into being a better partner as well. We want to be able to take some of the heavy lifting off of teams who are developing pipelines and interacting with the data so that they're really doing science. And we want to be ready. This infrastructure that we're intending to build has to be ready for the large volumes of stuff coming at us. So all of that is the inspiration behind a multi-year project that has not started with me. In fact, it's been around for many years, and the Keck Science Steering Committee has seen it in multiple different forms over the years, but it now has it lives under an umbrella which we call the Keck Data Services Initiative. And you could view DSI in the following way. Right now, the observatory's motto, or its unofficial motto, is on sky every night. But when DSI round 1 is complete, it should be on sky every night with the best data. And what that means is we have to have an end-to-end renovation of Keck's data flow. And I'll talk about what that means in a minute in sort of a night in the life at Keck. But it fundamentally requires not just that we have data reduction pipelines or an archive, but that all of these things know how to talk to each other correctly, and they know how to talk to the observer correctly, and what the observer intended, or for lack of a better word, the provenance of data is really important if we're going to understand how to get the most out of it scientifically. And we want to be more efficient on sky and faster to science. We don't want the hindrance to science being the archive or the pipeline. We want the hindrance to science being the science itself and the development of the algorithms needed to understand the data, not to reduce it. And we want to also have smarter data for our community and for the machines. It is obvious that one of the trends in data analysis going forward is going to be artificial intelligence, machine learning, and those kind of things. But those systems are going to require data to be understandable if they're going to be useful. And so we have to make the data smarter in a metadata sense for both people and for machines. What's the real goal of DSI? The true real goal of DSI is to improve the scientific productivity of Keck. Hilton alluded to this in his presentation yesterday when he showed the number of papers and how that's plateaued at a very nice number over time. But that really what we need to do is to take the next leap, which is leverage the fact that we've got a nearly 3-decade archive of data, that we've got an archive that can serve new data, and we want to expand that community and improve our scientific productivity. So I stipulate that improving our productivity means that we have to have better data. And what do I mean by better data? We want data that is planned ahead. That is to say that we know about the provenance of the data, we know about the planning that went into that data, and that is written down so that years later when somebody comes and tries to look at that data or reanalyze it, they understand what the plan was behind it. And that means also that the data has to be fully described. Currently, the way we write data down does not always have in it, for example, that this is observation number 14 of a 17 observation sequence with a 6-point dither or something like that. And that information is not always written into the data right now. And if you were to come back to that data many years later and you didn't have the handwritten notes of the observer at the time, you may not be able to understand it. Data has to be correctly calibrated. Our community calibrates the data to its own purpose for that individual observer. And if you were a frequent user of space data, you know that data from space is done very differently. There's very rigid calibration requirements to that data so that it is maximally useful, maximally scientifically productive. And we can do better here to guarantee that data is calibrated uniformly and correctly on the Keck end. And we want data that is quality checked. If you take an arc lamp exposure, for example, and you weren't paying attention and you move along and start taking your science, and it turns out that the arc lamp wasn't on or hadn't warmed up enough, then that data is potentially quite less useful. We want algorithms that look back and say, are the calibrations actually of high enough quality? And is the science data that's rolling off the telescope of high enough quality ready to do science? So we want to be able to check the calibrations, and we want to do quick look analysis of the science as it rolls off the telescope to make sure that it's high enough quality and that that quality is written to the data headers itself so that, again, years later, you might be able to understand it better. And data must be easy to understand and reduce. Keck instrumentation is very complex. More recent instruments have hundreds of header lines written to them, and we have to have a translation table between the gobbledygook that's written oftentimes to the header and the real world, and it has to be easy to reduce. And finally, speaking to the archive, it has to be easy to retrieve. The way that we retrieve data right now is that we hope that the headers are correct and can do loose associations of calibration to science data, but we want all of that process to be easier. So the 30,000-foot view of DSI is this. It has 4 key pillars, and I'm not going to speak to every little thing on this diagram, but what I wanted to emphasize is that there's a lot of pieces of DSI that are happening behind the scenes in how we prepare the data for ingest, how we reduce the data behind the scenes, and how we serve that to the archive are really a lot of things that the user won't necessarily interact with, but will require significant amounts of data of software infrastructure over the coming years. And that's really much of the main focus of the developments here at Keck and at Nexi, is to facilitate those aspects of it. And then the data reduction pipelines are largely being written by the community, by community partners. So the one thing that I'll say is that, you know, all the stuff that I talked about data sounded a lot like a queue system. If you've used a queue system on the ground or in space, this is most definitely not a queue system. Keck is and will be a classically scheduled observatory. And even though we intend to do a lot more planning around the data and calibration, that does not mean it is a queue system. So let's flesh that out a little bit more. It's not a queue, and so we do not plan to limit the flexibility of observing modes. Just because DSI has requirements around calibration and execution does not mean that we have requirements that strictly restrict some of the observing modes that we currently have in place. And the role of the observer and of real-time decision-making when the observations are executed is preserved. You can still decide at the last minute to change your target. There is nothing in DSI which forces you into a specific set of observations in a certain way. And to address a question that I get oftentimes from the community, which is, can I turn it off? Yes, you can turn it off. This is meant to be a layer upon which one interacts with the instrumentation and with the archive, and it is not meant to be the only layer between those things. And so you can turn it off if you really, really don't like it. I don't want to get into really the background nuts and bolts into DSI, and I'm happy to do that at length at another time. Instead, I think I wanted to walk folks through what we envision as a night in the life of an observer who is working with the DSI system fully in place. And then I will get to the more important part of this session, which is when I hear from you folks. So here's sort of a night in life, and I'd like to thank Luca for flowing this out for me, because he did a much better job of it than I would. So here's the DSI experience in a nutshell if you're an observer. And I apologize for the small text. So in advance of the run, the observer might define observing blocks, and an observing block just says, what is my target? What is my instrument configuration? And what is my observation built out of? Is there a sequence of observations? Is it just a single thing? Is it a nod along a slit? We intend to have templates for ABBA pairs or ABAB or dither modes. And all of this would be submitted over a web tool. So you can do it just from your web browser and is submitted to a database that resides at Keck. You can say this sounds like a queue, but no, it's not a queue, because all that's being done is that the blocks are being identified so that time of execution, you can just pick your block and hit go. But the key thing here is that you, the observer, are the ones who are hitting go. In the afternoon of a run, if you have put in your blocks into the database, the blocks are viewed by the calibration manager and says, aha, you're intending to use the following 3 gratings on LRES. I am going to go ahead and spin up the flats and arcs required at the exposure times required to give me the appropriate signal to noise to execute the calibrations on that. If you have ever used KCWI, for example, this is what happens with KCWI. You just set your settings. I want to use the medium slicer and with the medium grading, and you click the one button and it goes off and it takes the flats, arcs, and various other things that it needs. And so we're envisioning a very similar system for all the instrumentation. And then at night, this is where the classical observatory shines. The observer just chooses the observations they want and sends them for execution. And once in the execution manager, the observation can be changed. Just because something has been driven by a database that is selected by the observer doesn't mean it can't be stopped. You can stop the sequence, you can set a different observation, you can create a new observation block on the fly. These things still happen in a classical mode, and apologies for the typos. During the observation, the individual blocks can be stopped, started, repeated. A good question is, what about the interplay with the observing assistant? Acquisition, alignment, and those things that happen prior to an observation is actually a block that the OAs will be executing. And so the wonderful thing about this, in terms of acquisition, alignment, and all that, is that every single block of the observation is written to the headers. So that, for example, if guiding was lost briefly, and guiding was off between a certain set of observations, because that's part of a block, that information is now going to get written to the headers instead of you hopefully scrambling it down in your log file. And this will also be helpful for the OAs at night for it logging issues either with the telescope or with instrumentation, because they can just copy and paste right out of the blocks what was happening. During the night, the fun thing, and this is a big difference between how we currently observe, is that pipelines running at Keck will be monitoring for new data. They'll just say, is there a new science file? If so, do I have the cals for it? If so, I'm going to quick reduce it and show you on the screen what it looks like. Raw and quick look data will be ingested into the KOA in real time, so that within minutes of an observation being executed, the raw data can be accessible to anybody who is part of the observing team who has access to the KOA via a web browser. And then quick look data will be ingested as fast as it can be produced. And during the morning, if you created a block that was did not have the cals run in the afternoon, new cals are provided, and then the pipelines that were doing the quick look switch modes and re-reduce the entire run for the night and push that data to the KOA. So this is the part where we get to the Q&A. This, just a bad meme joke here with DSI is the future, changed my mind. I wanted to interact with you folks in three lightning rounds, if you will, of interaction with DSI, which is, in rough terms, with the system that I've proposed, what do you expect as an astronomer out of a system like this? What if you were to be able to write down, when I come to, as an observer, I expect the CALs to be robust, or I expect the quick look data to provide the following metrics. And so that's one of the questions that I'm going to ask. The second question is not what I expect, but what do I require? What is the minimum barrier to, what is the minimum bar to meet as an astronomer who's using DSI, that if you don't meet this bar, you would just prefer to have the system as it is now. So this is what you expect, but this is really what you absolutely require. And the final part is, what do you reject? What would you not want this system to do? What would you say that this is, that certain aspects of this are just not what you want and would not be good for your observing experience? And the only thing that I'll ask you to do in the back of your mind is also to expand the horizons beyond, a little bit beyond exactly what you need for your science, but to close your eyes and imagine what a student, a postdoc, an astronomer 5 years later who goes into the archive and pulls up your data is interested in doing, and what DSI did to help that future astronomer get what she needs. So I'm gonna open it up. I'm gonna stop the sharing here and just have us go with lightning round question number 1. And I will, let me see how many people are on. We have quite a few people. So what I'm gonna do is have people raise their hand to provide commentary for lightning round number 1. And Carrie is leading the march, already has a hand up. Carrie, go ahead.
Hey, John. So I actually had a question related to the morning calibrations that you mentioned.
Yeah.
So would that in principle be something that you said it would check for calibrations for new blocks that you created during the night? Would that also do things to check for blocks that you changed during the night?
Yes, I view those two as equivalent. So if you change a block that requires a change in configuration to the instrument, where something like I changed the slit width and so I need new arcs or something like that, then yes, it would in principle recognize that and produce new CALs based off of that.
Okay, thanks.
Yeah, Lauren, I see your hand up.
Thanks, John. This sounds like a really cool initiative. I'm curious about programs that tend to chase stars near the horizon. So for instance, if someone were to set up a block and then one of the stars of the block maybe was up when they were planning on it being up when they created the block, and then it sets or just gets to high air mass, how would the system deal with that?
Oh, I think the system would look at the observability of things. So you can take the blocks and plug them in in a similar way that you would do the night planning yourself. And remember that with the exception of things like cadence observing, which I know you and Andrew, who I see are both on the call, are probably quite interested in, there you would be setting up blocks that really it's a sequence of targets and you go after them as fast as you can. And some special care will have to be taken, I think, for optimization around the ordering of the observations in the block. And this is actually where I'm gonna lean pretty heavily on the exoplanet community for guidance on optimization around block execution, because I recognize that going after many targets in a night is going to require an additional layer of optimization of the blocks. Especially if we're in a cadence mode where the PI isn't the one doing the observing. I don't know if that is really where you're going with the question, Lauren.
Yeah, pretty much. I mean, something we saw with the automated planet finder, which is a robotic telescope where we do these kinds of observations, and it's sort of all pre-scripted, right? One issue that comes up is, right, what happens when you've got some target that you want to get and then it sets or whatever. So it's sort of this like edge case at maybe the 10% level that we just kind of haven't optimized yet, I'd say.
Yeah, but at the 10% level, I mean, I can see Randy on the call. If we had a 10% fault rate every night, we'd be unhappy. So,
yeah, exactly.
I think this is definitely, so one thing I've neglected to mention is that throughout the development of DSI, especially once we start to get into instrument-specific definitions, this is the part where we're really going to reach out to the community for the edge cases, because we can leverage two things. We can leverage the deep bench that the SAs have because they've seen it all happen as they've been working with folks every night. And then we know the places where the development is going to be the hardest. And so we would reach out to you folks and have you prototype things for us and look at those systems. So, definitely keep things like that in mind when we start to reach out to the community with early prototyping. We intend to prototype early and prototype often with community input.
Yeah, that sounds great. Supervising the prototypes, I think, is the way to go.
Yeah. Andrew, I see your hand up.
Yeah, this is somewhere between a comment and a question, so you'll have to interpret it as you like. So the issue is, of course, there's many Keck teams that have their own internal infrastructures for dealing with data. And they have all sorts of procedures and so forth. And I guess maybe the suggestion side of this is to construct the observing planning and the kind of data retrieval through COA with an API in mind, instead of having just one way of doing it with, say, a web page where you have to interact with it in that particular way. I think this would allow all of the groups that have kind of longer term programs to raise their game in a way that is beneficial to those groups, and we can get the most out of DSI.
Yeah, so Andrew, I completely undersold the way in which people are going to interact with the KOA on DSI. And my interaction style with the KOA is, I go to the web browser and I click on one or two files, and that's how I do it. I see that Bruce Berriman is on the call, and the KOA team is already developing a number of ways of interacting with it that you could do scripting, you can do multiple things, but I can let Bruce speak to it for a few moments if you'd like to, Bruce.
Yeah, thank you. We're, as well as supporting fast access to data, we are in fact modernizing and updating our query infrastructure in the next year or so. We'll be actually doing this independently of the DSI. It's part of our core funding from NASA. Most people nowadays, they would access the data from the web page. What we really want to do is provide a lot more flexibility in our interfaces. We are in fact developing a Python client, which we hope to release in the next few days or so, certainly by the end of this month. This will give people an awful lot more flexibility in accessing data. We're also building that particular client on top of a VO-compliant table access protocol service, which will give people huge flexibility in building their own interface if that's what they want to do. So once we've released the new client, we would really like to get feedback from the community on what kind of services, what kind of search engines they would really find most powerful. And a Python client, in fact, is one of the most requested features we've had from users, as you might imagine. But we regard this as only the beginning of Python services, and we would like to extend them and make them much more powerful. But to do that, I think we would really like to get the user community's feedback on requirements and expectations.
Mm-hmm. Thanks, Bruce. Brad, I see your hand up.
Yeah, so I actually going to make two comments. Bruce's discussion of what COA is planning to do sounds fantastic. But I would like to kind of reinforce Andrew's comment about an API, especially on the front end. I was immediately thinking about the use cases for some of the various kinds of science I've done or have done in the past. And you start to think about, I want to construct observing blocks. I automatically construct, based on my Deimos mass back in the day, observing blocks and observing schedules for the entire night. And the idea of then having to then click into a web form and fill in, by hand, or ideally at least somehow having it reference the FlipMass database as an example to pull the information as appropriate would be nice. But even better would be to have an API where I can interact with the backend directly through, some sort of web moderated system, web moderated calls would let, people who have, as Andrew says, long running big programs where you do large surveys, a much more efficient way of generating all these observing blocks.
So at risk of getting a little bit in the weeds, Brad, the way that we're looking at doing the observing blocks is we're basically creating these YAML files. And so an API of what you could roll your own thing. If we tell you exactly what the YAML files are being expected, you can develop it however you want. And then presumably what we would need to do is to guarantee that how you bring those YAML files into our database for it is secure and consistent. So I think that's the rate limiting step there, is to make sure that it comes into the database right. But these are not intended to be very complicated things. They may have a lot of entries to them because different instruments have different layers of complexity in all those modes. But the flavor of the stuff, the web interface is mostly for new and not so great experienced users. I mean, and is inspired by things like KCWI. But I think when you start to see the type of files that this interface is spitting out, you'll be able to, I don't think you need a complicated API. Is really what I'm getting at with it. I didn't want to get too in the weeds with it.
But then, having a set of example tools for, here's your LRIS night, here are your masks, blurp, then here's the example, having things like that would greatly aid, I think, a lot of folks. And that's
an excellent point. And I forgot to do this at the very top of the discussion, which is that we have, the Slack channel for this breakout session. And Brad, if you wouldn't mind just writing that down as a single sentence or a couple sentences in the Slack channel so that I can capture it, because I'm trying to manage the Zoom at the same time, so I'm not going to be able to take great notes. Vivian, I see your hand up.
Yes, but I think Carrie's hand was up before mine. So does she want to ask her question?
Oh, I'm giving people who haven't had a question chance yet a chance to go first.
Sure, thanks. So I was wondering, maybe a tangentially related question. So in the spirit of standardizing all of the data and making the data useful for generations to come and whatnot, some science programs simply need flux calibrations and some might not. And that would have different requirements on whether or not you need standard stars or that sort of observations during the middle of the night. So is that something you're going to be enforcing on everybody, regardless of what the science requirement was for the program, to take up some time for standard star observations or not? Yeah,
so that's a really good and important point, Vivian. So our intent with calibration is to is twofold. First, we recognize that there are non-standard calibrations that many observers do to eke out every last photon or deduce flats in a special way, and we will not place any requirements on stopping people from doing that. Now, things that occur during the night on sky, I don't want to set this as completely official policy because I'll have to think about it, but my sense is that I would not require flux calibration. So taking time away from the night to do specific cals. Now, there may be the issues with tellurics that we have to think about a bit for the IR instrumentation, but some of the pipelines, or, if you ask Joe Hanawi, he'll claim that Pipette doesn't need tellurics. I think it's a really good question, and Vivian, if you could preserve it in the Slack for me, that would be quite useful, is to think around policy around flux calibration. But it's a good point because it takes sky time, and we don't want to impinge. We really would like to make a system that is easy enough and simple enough to use that people are going to want to default to it, but we don't want it to be obtrusive on the night. And so I'll have to think about flux calibration, but if your science program doesn't require flux calibration, ideally one could either interpolate a flux calibration thing if it was a standard mode of the instrument, or we can think about that ways of trying to address that in pipelines. But it's probably not going to be our policy to force flux calibration, which is a really good example.
I mean, the counter argument is that maybe if you have the files or the data available, then it might be useful for long term if other people wanted to use it for other reasons. But
no, And that's a very good and important reason to want to do it. I think one thing we may not have done well enough on the data reduction pipeline side is to get, 90%-ish quality flux calibration based off of archival things and stepping through the parameter space of the existing modes of the instrumentation. And one of the preamble data sets that we could take with this in mind is to try to get, the sensitivity function data that we would need to generalize flux calibration at, not perfect accuracy that you would get night to night by taking the star, but good enough to get, relative flux calibration out.
Yeah.
So one middle ground solution to this would be to auto-generate a block for flux or teleric calibrators that is then easily available to the classical observer.
Yeah.
And sort of say, hey, if you've got 10 minutes in twilight, go hit this bright star. But yeah, I don't think we're going to force anybody to spend dark time on things that they don't need for their science.
Okay.
Carrie, I'm going to go to you, and then Andrew, I see your question in the chat, and I have an answer around that.
John.
So Carrie.
So yeah, I just actually wanted to say something which was more like directly answering your question of like what I would expect from this and what I would need. And this, a lot of people have mentioned this as well, like with you and Brad talking on like, for such a system, I think I would want something that would be robust enough and it would be easily implemented. And from what you have been discussing, that seems like that's what you guys are aiming for, such that, as you said, if it's something that's easy to use, that we would, as observers, we would default to that to, make our lives easier and to make, sure everything has been recorded to headers and things like that. And I think as long as it's, simple to use and it's well documented, I think it sounds like a really good idea.
Yeah, I think the example I'll continue to give is KCWI. When you use KCWI, you could, in principle, set the instrument to all the different settings that you need to do and take individual exposures for all the calibrations that you need to do. Or you could hit the 3 buttons that says calibrate this thing, go, and come back in an hour and have all the cals that you need. So we want to be able to enable the former, but hope that people prefer the latter in terms of their interaction with these things. Now, there are going to be specialty things for which, at least in the early implementation, DSI is just not going to be able to do particularly well. I can think of vector vortex coronagraph modes on NERC2, or things involving the pyramid wavefront sensor, or very elaborate modes of instrumentation that we may not be able to make that type of interface for. The simpler the instrument, the easier. So, NIRES is going to be much easier, I think, in principle, to plug into and KCWI into DSI than perhaps some things like weird modes in NERC2. So it will be building up over time. We need to build the underlying infrastructure and have a couple of test particles. Ideally, our intent is to prototype an optical instrument and an IR instrument in the first rounds end to end through this to make sure that the system works, and then start to expand that out for other instruments. Andrew asked in the chat, is there an intended policy for the proprietary period for calibrations? Will user 1 have immediate access to user 2's calibrations, i.e. to see time series evolution of systematics? This would need to be done in a way that respects proprietary period for science data. So Andrew, we're already building a policy around calibration data right now, where if the cals do not have any target identification in them, so an example of something that has target identification in them is a flat field for a mask that has the RAN deck of the slits written to it. That calibration would remain linked to the proprietary period, but a dark frame from that same instrument could have 0 proprietary period. So you can imagine that if you're taking long slit flat dome flats with LRES, that does not give away what your observing program was. But anything that has identification directly to the frame. Now you have correctly surmised that because we want to understand the provenance of the cows, we will do the heavy lifting on our end to make sure that those things which should remain proprietary do, and that there will be various layers of visibility therefore in the things. And that's going to be a difficult piece of homework on our end to guarantee that the way that stuff's ingested into the KOA preserves that proprietariness. But we're paying attention to that. So I might, for funsies, flip all the way to number 3, because I'm just as interested in things about this that people really hate or are scared of, so that I understand them and do my best to either make you hate it less or do what I can to amend our plans for the system, because we're in the design phase right here, and so we can be as responsive as possible to your concerns right now. Andrew, you got your hand back up?
Yeah, so I guess one general comment is this all sounds super and I'm really excited, but it has to work well. If it's clunky, then it's going to be, I think there will not be a great appreciation for it. So some observatories do queues better than others. And I know we're not moving towards a queue, but maybe understanding what makes the ones that do it well work efficiently, I think is something to pick up on.
Well, so Andrew, I would love examples of things that aren't done well. And you don't have to rattle them off here. But understanding the things that are not done well will help me shape significantly the things that can be done well here. The other thing that I think is important to point out is because it's really an end-to-end system, in all likelihood, DSI will not be ramped out for all instruments at once. In fact, it's very unlikely that it will be ramped out for all instruments at once, just because we want to be able to have the quick look pipelines and the science pipelines running and all those pieces. That will provide us the ability to continue to iterate and understand where the problems are. But I have a timeline in mind for. Well, in fact, I have not just in mind, but I have a timeline of, which pieces need to be done by when. So, much of the infrastructure is instrument agnostic, but some of it most certainly is not. And so where we do the prototyping will be things that, we'll be building up the infrastructure on one side and then the instrument specific stuff on another. So I'm really going to look forward towards to prototyping this frequently in the community to understand what is clunky about it and if it's perceived as clunky. But it will not be, I'm not going to magically show up one day, flip the switch and say DSI is on, deal with it.
Yeah, I think maybe to be a little more specific, it's the user interface side which is really important.
Yes,
and
I completely.
It's just to be a little bit specific. I personally avoid observing with Gemini because the setting up the phase 1 and phase 2 plans is just so time consuming. It's 1,000 clicks. And if I could do those observations somewhere else, I'll do that. And I think I'm probably not the only person who has that experience, and I'm sorry to be being specific about one observatory, but I think we want to avoid that.
Well, it's important for me to know what annoys you from any observatory. So please feel free to work with us.
So I'm a little curious about this because, even within the existing instruments at Keck, there's a lot of different design philosophies around the user interface. If you look at LRes and high-res, they are interfaces that say, you're an astronomer who understands spectrographs. There's a motor that controls this mechanism. Tell me where you want that motor to go. You look at some of the other instruments, KCWI being one example, but say MOSFIRE being another, they're modal. It says, you want Mossfire to be in K-band spectroscopy, you know, rather than saying, I want the mechanisms here, I want this filter over here. This will sort of take that a little bit one step further. So if you look at Mossfire, which I'm really familiar with, there's a lot of sequences that you just repeat ad nauseum if you're observing with Mossfire. You go dark, you set this alignment mask, you execute it. We can turn those sequences into scripts and make them really optimal. You know, I introduce a lot of new observers to Mossfire, and it's a little bit painful sometimes because I know I can get the time between exposures down a lot, you know, quicker than they can as they're learning. So I think there's a lot of opportunity for us to create efficiencies there, but it does sort of disconnect you from that idea of like, I know how a long slit spectrograph works. I want this mechanism over here to be in this mode. So I'm just curious if you have a feeling as to whether that's one of the core problems, or is it just literally good UI design?
I think it's, so first of all, I would separate the user experience as an observer at the telescope. So that is the interface with the instrument, from the interface which drives the planning of observations. And my complaint had more to do with the latter. So for example, if you're in a program that has, you know, 100 different targets, you have to go through and do sort of pull down menus for every single one. And it's an exercise in repetitive strain injury. That's an obvious thing that I think we want to try to get away from. So some way to sort of, and we already talked about having templates, but even be able to sort of modify a group of observations in bulk to apply the same change to all of them, I think is really helpful. There's also a certain rigidity to the Gemini system that they're trying so hard to prevent you from doing things that they think you're not supposed to do that they're tying their hands behind their back sometimes.
Okay. Well, I mean, you and I should probably talk offline, Andrew, because I know for programs like yours with very large sets potentially running cadence mode, we don't want to have RSI. So
this is DSI, not RSI.
Well, yeah. Chuck, I see your hand up.
Yeah, I was curious about whether there are going to be improvements in the metadata for understanding what exactly was happening during an observation. Because if you were pulling stuff out of the archive, you know, some instruments you could just, I mean, I guess I'm thinking about the big difference between routine observations where you're doing the same thing over and over again and there's no real challenge to acquiring the target and all that kind of thing, versus things where you got to figure it out as you go along because you don't have it in the mode yet that you are ready to put it into, you know, a scripted production. And we work in that mode a lot.
Yeah.
And the other thing is, a lot of times I notice things that are not right that would otherwise have been unremarked by either the OA or anybody else, because I'm paying attention to like a million things at once. And, you know, I don't know how I would know anything about a data set that I took out of the archive because there's just not enough information. Maybe it would improve. I guess I'm just, what do you do about, you know, the 15 or 20% of the data that are crappy?
Yeah.
You know, you end up wasting a lot of time trying to get blood from a stone on crappy data.
Well,
you know, and that's going to be a big challenge for the DRP kind of stuff too. Yeah,
speaking as somebody who produced Kodiak's DR1 through 3, I know exactly what you're talking about. Our intent with this is to write absolutely as much as we can in a metadata sense, and including things like what the telescope was doing and how it got there, including things, and we're trying to figure out the best way to ask the user upon data read or upon quick look to identify, is this what you expected? and hit a button that says, is this what you expected, right? So for example, just take an art, part of the problem with going into the archive is you don't know if the cals were done correct. It's identified as a flat, but unless you know that flat field really well, you don't know whether or not it was the right signal to noise or things like this. Now we can set the minimum. We are working with the DRP people to identify what we would call the correct set of calibrations for standard modes, so that when the data hits the disk, we can go in, look at it, and say, was the signal to noise at this wavelength what we needed and expected it to be? And that will be written as QA flags into the metadata, into the header.
Yeah.
And then ideally, after the exposure is done and you get some quick look, say, of a long slit exposure, it says, is this roughly what you expected given the things, or, do you need to add a comment to this that says, oh, it's probably because of the cirrus, right? Or various other things in there. So we want to try to be as robust as we can. We're not going to catch 95. We're not going to catch 99%.
Like I think the calibrations are the things that nobody ever has time to check because you're trying to do everything really fast before the sun rises or something like that. And there are a lot of things that go wrong. The calibrations fail a lot of the time for some reason or another. Like a lot of times, well, let me give you an example that's concrete, and Josh will know what I'm talking about. To calibrate a mask with Mossfire, you have to do this thing that puts a slit in two slits that puts the star in two slits that are spaced apart from one another. So it has to do a dither, a nod within each slit that are separated by 45 arc seconds. But most people don't know, and most of the OAs don't take into account that you'll never get the thing on the slit if you don't have guiding working and you don't have a guide star at the middle of the guider almost exactly, or else it just goes flailing around. And, I would say 80% of our calibration stars have no flux in 3 out of the 4 exposures or something like that because the telescope just did something crazy. And it doesn't know that it's done that.
Yeah, okay, so in that case, Chuck, I think we'll have some resilience against that because the observing blocks will also include the pieces like alignment and whatnot. So if you knew that this is supposed to be one of those calibration stars, it will have, as part of the other side here, oh, this has to be in the guider this way and ... right? So this will actually be helpful for that because it's going to use as flags to say whether or not the following things that were expected were done. So, Now, so what will be most helpful is when you get that first read and the star isn't doing what you're expecting it to do, is if the user can just hit, no, this is not what I expect. Then the archive is going to have a lot more utility in the sense of saying, wow, okay, yeah, I forgot to turn on one of the 4 arc lines that I need to do to get ESI properly calibrated.
Yeah, I would say that there's a general problem with the magic guider system that it doesn't really know when it's not guiding anymore because it finds a centroid on whatever and keeps happily trying to find a centroid, and sometimes it runs off and it never says we lost guiding.
Well, my hope, Chuck, is that no matter what, even if it won't be perfect, we will have a much better logging of things like, oh, we lost guiding, and so you can put that into the data itself.
Yeah.
Now, we're not going to like I said, we're not going to capture everything, but I think we're going to capture significantly more for the sake of the archival utility. But what we're going to need is the joint experience of the OAs, the SAs, and the observing community to optimize and get it right. And so that's why community prototyping is going to be an important part of this.
Right. Yeah. So this is one of those areas where there's a lot of really, really difficult problems, but there's also a lot of low-hanging fruit that is not that hard to grab. And so one of the concepts that we're using when we're talking about like the instrument scripts is pre and post conditions. So before you do step X, you have to, be in the state you expect. And when it's done, you have to be in a state that you expect at the conclusion. And one of the things that you can build into that is, for example, if you're taking a calibration set and you just took arc lamps, are there some really bright lines in this data? And are there, getting rough, estimates of signal to noise that you expect. And so I think there's a lot of things that we can do in that regard. And some of that's going to be a bit of a stretch because, again, some of these get really complicated. But that's one of the areas where I think we can really catch a lot of these problems, because you don't necessarily need a human to look at these to catch the problem. It's usually pretty apparent.
Yeah, so much of this is exactly what Josh said. In CALs, I mean, especially if you're taking the CALs at 5 in the morning and you're sleepy and you started the flat, you started the flat before the grading was there or something like that. And you maybe wrote it down on your piece of paper, but it certainly wasn't written to the header that way. So yeah, a lot of pre and post condition checking is going to be quite a useful utility. I see we're at the top of the hour, and I wanted to give people time to stretch and go in between sessions. But I think that the major thing that I want to request from folks is either here in Slack or emailing me or Josh or Luca or Bruce. Questions, concerns, recommendations. We're really at the stage right now where we can influence pretty significantly how we plan on building many aspects of this. In other places, we have to be more rigid for some of the deeper infrastructure pieces, but for things like the user interface, and particularly since we're developing this in an agile-like environment, we're developing it around user stories. So, basically I can ask the question, as Chuck Steidel, I expect that this, and this happens for my observation. And that's how I can build the software around it, is the language of user stories. And so we're going to be reaching out to folks. We've identified some folks in the community already, but if you want to be a part of this, please let me know. It'll just mean that we're going to need to interview you about how you observe and what you expect out of a system like this and what you don't want this system to do, because I know some people will not want the system to be, running the show in certain places. So understanding that is really important. Are there any last minute comments, questions, or whatnot? But I'd like to give folks time to take a break between this and the next session. Hearing none, seeing people already starting to leave. I think I'm going to draw the session to a close. I'd like to thank everybody for coming and look forward to hearing what you can tell us that you want to see out of this, because it's going to be really exciting. Thanks.
Yeah, thank you, John.